Hello, I'm Hao Jintrom and from High Second Learning Team, and today I will share something about the UEFI on HiKey and the HiKey 960. For this presentation, I do not introduce the UEFI on HiKey with all modules because the firmware is already enabled for a long time, and Leaf, I think he has already have a lot of presentation on the UEFI. So in the presentation, I only focus on the change between our release and what we will do for the upstreaming. As we know that the indicator is an implementation of the UEFI, and for the second item is our release. In this release, we have two Git repository. One is for the indicator, and the other one is the platform package. But the open platform package is not the ones that are accepted by the indicator. We have three Git repository. The second one is for the platform drivers, and the third one is for the binaries. And for the HiKey and the HiKey 960, we are still in the process of upstreaming. Now we supported two chain. One is for the GCC, but because of some bugs in the GCC, the version should be the 7.1, and we also supported the LLVM. We should specify the clans at least for the 3.9. If people want to build the firmware by himself, we also have the sample scripts to handle it. In our implementation, we used the device tree. Actually, for the indicator, we can select either to support the ACPI and the device tree. But as we know, in the ARM embedded SOC, we don't have the PCI bus and the ACPI, so we will choose to use the device tree, and the device tree can describe the hardware capabilities, and it should be transferred to the Linux kernel by some pointer. In our HiKey implementation, in initial, we store the DTB at the end of the kernel image. I think it's used wired commonly, and we also support to store the DTB in the boot or root device partition in our releases. I think it's only for the early stage. Now for the upstreaming, we changed the policy. The DTB could be built into the firmware. It's filled in the section raw. We just need to write this kind of information in the HiKey.fdf file. And we rely on the DT platform driver. And in this implementation, we only support one DTB. So we always put the DTP file from the latest kernel and store it into our Git repository. In the UEFI, we have the parameter of the EFI system table. The system table contains the pointer to the runtime and the boot time service table, and the DTP is also a part of the EFI system table. So we could use the function of the install configure table that belongs to the global the boot service. And from the view of the EDK2, the kernel is just an EFI application. So UEFI could boot the kernel directly. For example, we implemented this behavior when we tried to boot the Android kernel. And the kernel could also be loaded by the bootloader. So we use this way. We use grub to load the kernel. For example, if we want to boot the system for Debian. So this is the code in the kernel. So when we enable the config EFI, this entry is the first entry of the kernel. We can find the core. This is the parameter of the system table that is specified by the UEFI. And in the real implementation of the EFI entry, we can find that it will face the parameter of the DTP pointer from the EFI system table. And then kernel get the DTP, and it will get more information about the hardware. And for this one, because we want to support the multiple driver in supportable multiple device instance for the same driver. The reason is for the embedded system, we always specify the register space by the PCD value. But for example, if we want to support for example, in the real silicon, we may have the EMC, we may have the SD. They are using the same IP, but we don't want to use multiple drivers. So, oh, sorry. Oh, sorry. We don't want to use the multiple drivers. So we share we tried to add a new device driver that is the non-discovery device driver. This driver actually is derived from the non-discovery PCI device driver. But this driver is only focused on to simulate the PCI bus, because in the HiKey we don't have the PCI bus. So we use this one to claim the different register base of the EMC and the ASD driver. So here is two examples for the ASD driver. The first one is about the x86. Here is the framework of the SD driver, and we and this is a PCI driver, and but in our implementation we have the two different drivers to implement the similar feature of this one. Because we only in previous slides we said that we will build one DTB into the UEFI, so it only means that we have to use one DTB to support multiple versions of the hardware. For example, for the HiKey 960, the hardware is a bit different. The GPR pins to the LED are different, and the GPR pins to the USB hub are also different. Because we want to distinguish the two different hardwares, the ADC convert is added. We can read and the ADC converter linked to the version resistor. We can read the value and identify which hardware version we are using. So then we could replace the different property node into DTB according to the hardware version, and all this operation is based on the FDT-lib. And we also did some enhancement in the boot manager. As we know that in the UEFI that is designed for the server first, so every boot options could be selected by the console, but for the this also have a requirement. This also has this also means that when user install the OS, it will create the boot options. But for the embedded system, we hope that all boot options should be created before user use, since there is no OS installer. So we add a new protocol, the PlatformBootManager protocol, into the PlatformBootManagerLib. And as we know, the main difference between the EDK2 and the U-boot is based on the modules. The all UEFI driver are built as modules. So if we want to communicate with our platform driver and the EDK to the common code, we need based on the interface. We needed to install the PlatformBootManager protocol into the platform driver, and in the PlatformBootManagerLib, we could get the function call from the interface, and we can get the detail of the boot menu and the hotkeys, and register it into the boot manager. From this, so this is in implementation in the PlatformBootManagerLib. We can find in the function call, it will try to load the boot options from the variable storage. But in HiKey, in the latest HiKey, we didn't implement the variable storage. So we will try to load the predefined boot options. So as we know that the variable storage is used to store some variables when the OS installer try to install the whole OS, it will create the boot options when it's finished. And when all boot options are loaded, we will call this function to register into the boot manager. For this driver is also appended because it's related to the boot manager. For the server side, people always select the boot menu by the keyboard, and he will get the view from the console. But for the embedded system, people hope it could boot as quick as possible. So we need to add some shortcuts, such as we use a GPIO switch. For example, if the switch is on, we can boot to the fast boot mode, or we can boot to the normal mode. And in the boot manager, it will just receive the keyboard event. So we added the virtual keyboard driver to simulate the GPR setting into the keyboard value. And then this is the interface of the protocol. And for the Android image support, we in the latest version, we supported the gzip kernel. Initially, we just supported the raw kernel. Now we enhanced with the gzip kernel. We also added the RAM disk and then the non-RAM disk support. For this, it means that we can also attach the DTP still in the end of kernel to be compatible with the old version on HiKey. We also could use the separated DTP that is built in the UEFI. All this implementation is contained in the PlatformBootManagerLib. And this is about the upstream status. We already upstreamed the boot manager, virtual keyboard, boot image, but we still left some components for, especially for the device driver, the SD, USB, and the UFS. Any question? Thank you.